Um, Hello everyone. Welcome to this video where I go over the formulation of a simple maximization problem. So we have done linear programming formulation of the furniture problem in the introduction video. I'm going to look at another simple maximization problem, and I'll also post a different video of a simple minimization problem. So the idea for this week is to go over linear programming formulations. We'll be looking at the solutions in the coming weeks. So here's an example from the textbook. This is a company called Par Inc., which manufactures golf equipment and supplies whose management has decided to move into the market for medium and high priced golf bags. So Par Inc.'s distributor has agreed to buy all the golf bags that Par makes over the next 3 months. Now, each of the golf bags that are made will require to go through it's required to go through 4 different departments or 4 different operations: cutting and dyeing the material, sewing the material, finishing it, inserting the umbrella holders, cup separators, etc., and of course inspection and packaging. Now, the time and hours for each of the 2 types of bags that you want to make to go through each of the 4 departments is given here. So it can take 7/10 of an hour for the cutting and dyeing department for the standard bag, half an hour of sewing, 1 hour of finishing, and 1/10 hour of inspection and packaging, while these are the times for the deluxe bag in hours, right? So that's something to keep in mind. Now, we also know that the director of manufacturing estimates that there are 630 hours for cutting and dyeing available, 600 hours of sewing available, 708 hours of finishing available, and 135 hours of inspection and packaging available. Now, as you saw in the furniture problem, these hours can be estimated based upon the number of people you have full-time, part-time, and the number of hours they're working part-time, and so on. Now, further, we also know that for every you make $10 in profit for every standard bag and $9 in profit for every deluxe bag that is made, right? So given that that's the case, let's formulate this problem. So let's write, set up this problem, come up with decision variables, come up with the objective function and constraints. Now, let's do that. So here is the formulation for the problem. So what I'll do is I'll open up a Word file where we'll go through all the steps one by one, and then we'll go through the solution. We'll go through the solution procedure next week. Right? So let's open up a Word file. It's the syllabus right there. Okay. Now we know that there are 2 types of bags that we're making. So, and we know that the decision variables that were used here, so let's use the same decision variables. We'll use S for standard bags and D for deluxe bags. So the decision variables are, it's always important to clearly set out what the decision variables are. So you say S, don't just say that S is standard bags, you say S is the number of standard bags, and D is the number of deluxe bags. Because sometimes you might get confused as to what your decision variables are, especially when you're doing finance sort of problems. You might have money, you might have percentage of something. So there are many different ways you can look at the same problem. So it's very important to know which kind of variable you're looking at. Okay, so that's step 1. So step 1 is always decision variables. Right. Let's look at step 2. Step 2 is the objective function. So here the objective as is clear, is to maximize profit. We know that we'll make $10 of profit for every standard bag and $9 of profit for every deluxe bag that is made. So we can write the objective is to maximize profit. Let's say maximize $10 times the number of standard bags plus $9 times the number of deluxe bags, right? So 10 times S plus 9 times C. So that's the mathematical function that we'll be maximizing. So we're trying to find the maximum value for that function right there. And that's our objective, right? So the objective is a function. So I'm going to call this the profit function, which is the function of the variables S and D. So this is the profit function, which is the variable of variables S and D. So it's a 2 variable function, and that's my function, right? So that's the function that I want to maximize. So step 3 are the constraints. Now we know that there are going to be 4 constraints in this problem based upon the 4 departments that we are working with. So the 4 departments that you're working with are cutting and dyeing, so cutting and dyeing, sewing, finishing, and inspection and packaging. Those are the 4 departments. So we'll have 4 constraints based upon those 4 departments. Oops. Okay. So let's write the cutting and dyeing constraint. So in cutting and dyeing constraint, we know that cutting and dyeing constraint, let's look at the data. We know that it takes 7/10 of an hour to cut and dye a standard bag, and it takes 1 hour to cut and dye a deluxe bag. And we also know that there are 630 hours available for cutting and dyeing. So the total time that can be used for cutting and dyeing is 630, and it takes 7/10 of an hour for a standard bag and 1 hour for a deluxe bag. So let's put that down. So it's 7/10, right? For a standard bag. Oh, I don't have to write time, so you already know what that is. Plus, maybe we'll write times. Plus 1 times the deluxe bag. Actually, let's not confuse ourselves with that. Is less than or equal to the time that is available, which is 630 hours. Now, if you're not comfortable working in fractions, one option that you have is you can convert all the data that you have into minutes. Say, for example, 7/10 of an hour. So 1 hour is 60 minutes, right? So 7/10 of an hour is basically 42 minutes, right? 7 times 6, 42 minutes. And 1 hour is 60 minutes. In that case, if you convert this into 42 minutes and this into 60 minutes, you would have to convert 630 hours also into minutes. So 630 hours will be 37,800 minutes. So you can write the whole thing in minutes. So you can say 42 times S plus 60 times D is less than or equal to, what was the number again? 37,800. Now the reason why you'll end up with the same answer is because that equation and this equation are exactly the same. The only thing you're doing is you're multiplying both sides of this equation by 60. So if you multiply of the inequality by 60, so multiplying both sides of the inequality by 60, this gives you 42, which is converting into minutes. 60 converted into minutes. Again, 630 hours converted into minutes, which is 37,800. So if you don't like to see fractions, you could do that too. But in this case, the data is given as it is given, so I'm going to keep it that. Right? Okay. So now let's write the sewing constraint in the exact same way. So we know the data here. So sewing, 600 hours for sewing, and we know half an hour for the standard bag, 5/6 of an hour for a deluxe bag. So let's write that down. So half an hour for a standard bag plus 5/6 of an hour for a deluxe bag forgot to write the S. I don't know what happened there. Is less than or equal to 600 hours, right? That's the data. Let's make sure that that's what it is. Is less than or equal to 600 hours. So 708 and 135. I'm just writing the hours so that I don't have to keep going back again and again. Okay, so for finishing, it is 1 hour for the standard bag and 2/3 for the deluxe bag. So it looks like it takes longer to finish a standard bag. So 1 hour and 2/3. Again, you can always convert this into minutes if you want. 1 hour and 2/3. So there'll be 1 hour for a standard bag. Oops. Plus 2/3 of an hour for a deluxe bag has to be less than or equal to 708 hours. Okay. So 1 times S plus 2/3 times D is less than or equal to 708. And finally, for packaging, I think again deluxe bag is longer. It's 1/10 of an hour for a standard bag and 1/4 of an hour for a deluxe bag. So 1/10 of an hour for a standard bag plus 1/4 of an hour for a deluxe bag has to be less than or equal to 135. So all constraints that we have seen so far, they're all less than or equal to constraint. Doesn't mean that all constraints are. In this case, these are resource-based constraints. Resource-based constraints tend to be less than or equal to because you can either use up all the resource or you can use a part of the resource. You cannot do more than what you have. Now, in other examples that we are going to do see in this class, you'll notice that constraints can be greater than or equal to, or they can be equal to also, right? So apart from this, you also have the technical constraints. So technically speaking, you also need, so non-negativity, we will definitely impose non-negativity. So non-negativity means that all variables either have to be 0 or positive. They cannot be negative, so non-negative. And of course, integer constraints, again, just like I said with the previous example, we are not going to impose integer constraints because integer constraints make the problem much more difficult to solve. We will see integer programming problems later on in the semester where you'll notice that solutions don't automatically turn out to be integers. For this example, you'll notice that solutions will turn out to be integers because that's the way the numbers are arranged. But in many real life problems, numbers don't turn out to be integers, in which case you have to impose that condition separately. In this case, we are not going to impose that condition. Okay, right? So that's the formulation for the simple maximization problem. And I will see you in the next video. So in the next video, we'll talk about a simple minimization problem, and we'll set up the formulation for that. All right? Take care.